Okay, so throughout pre-calculus and the first parts of chapter 1, and then also the first two parts of chapter 3, we've been working on the slope function, and now we're using those concepts, tying it together, and finding derivatives. So you can think about 68, but 69, we're starting into finding derivatives for sine and cosine. And what they want you to do is find the derivative of sine and cosine using the formal definition of the derivative. So we'll start with using the formal definition, and that's basically the difference quotient, which is, I'll just write it up here, f of x plus h minus f of x over h, and then taking that limit as h goes to 0. So now it might be a little bit complex, but using the result you had in 67, which asks you to find the angle sum identities that you did in pre-calculus, we can find what the derivative of sine and cosine. So I'll find it for sine, and you guys can work on for cosine. It's the same exact steps. So this is something you're going to have to do throughout the course as well as on the AP exam. So sometimes they will ask you to use the formal definition of the derivative to find the derivative. So we'll use this definition to find the derivative of sine of x. So it is sine. F of x is going to be sine right here. So it's just f of, it's sine of x plus h minus sine of x over h, and that limit as h goes to 0. So this is where the trig identity or angle sum identity comes in handy, because we know that sine of two angles is going to equal to sine of x cosine of h plus cosine of x times the sine of h. All right, so I'll just continue that here, down below. Sine of x cosine of h plus cosine of x and sine of h, and minus the sine of x. So now we need to do some algebraic manipulation, and that's all over h. So the other thing we have to remember is from chapter 2, we learned some of the limits of sine of h, or sorry, sine of h over h as h goes to 0 is going to equal to do that right, and the limit of cosine h minus 1 over h as h goes to 0 is going to equal to 0. So we need to manipulate this so that we can use these known limits. So if we combine, or if I move this here, I'm going to switch the order here. So I'm going to move it sine of x cosine of h minus sine of x plus cosine of x sine of h all over h as a limit of h goes to 0. And then you can also do this for cosine using the cosine angle sum identity. So I'm going to factor out this sine x from here. Let me use a different color. So I'm going to factor out sine of x from here. And I'm also going to split this fraction up here as well. And then use it as two separate limits. So this is going to be sine x times cosine h minus 1 all over h, and the limit as h goes to 0 plus limit as h goes to 0, and this is cosine h sine h over, so I'm running into this text here, h. So using these known limits, we can see that this here, this limit here goes to 0 because it's the same as this right here. Cosine h minus 1 to 8 over h goes to 0. And this here, sine h over h, goes to 1. So what we're left with is cosine of h, and the cosine of h as it goes to 0, so the cosine at 0 is going to be equal to 1. So that as h goes to 0 just equals cosine of x. So f prime of x just equals the cosine of x. And you can do the same thing with finding the derivative of the cosine of x using the formal definition of the derivative and the angle sum identity for cosine x plus h, and then also using these known limits for sine h over h and cosine h minus 1 over h. Alright, so now with number 70, what they want you to do is find it graphically. So, and the reason they want you to do that, and the reason why the title of this is what is a thousandth derivative of sine, is that there's going to be a pattern that you'll find. And so what I'm going to do is I'm going to put it on Desmos, and what you have to do is put it on a whole sheet of graph paper and put sine of x. And let me turn this off real quick. So we know, so what I have plotted here is the sine of x, and the reason why I have these shifted down is that I'm going to use this as a axis of another graph. I just don't have a paper here that I can use to just using this as a graph paper of sorts. So this is another axis. Just ignore the -4. This is another 0 here. So if you want to look at this graphically, remember when we're doing this slope function in 3.1.1? Whenever you're coming up with a slope, this is where it's at its steepest right here. So that is going to be where it is the highest at its peak. So at cosine x, that's going to be at 1. So it's going to be here at the max. And then over here, it's when it's at 0. When it starts increasing and then coming to 0. And then decreasing, and then here as well. So right here is where we expect it to be 0, and then 0 here as well. And then again here is where it's at its most negative. So this point of inflection right here, where it changes from concave down to concave up, is where we expect the minimum to be. And then here again is where we expect it to be, to level out at 0. And then everywhere there's a min here, and then a max is where we expect it to be. I should be drawing it up here. So when I turn this on, it should fill in where I expect the zeros. And I'll just turn it on. Oops. Oops, what did I do wrong here? Oh yeah. So this is where it maxes out. So it should be 0 here. Then the point of inflection is, of course, where the maximum is, and that's why that should fill out. So now, what is the derivative of cosine x? So if I'm using this -8 as my axis for the derivative of cosine x, so this is f of x equals cosine of x, and this is f prime of x. Oops, sorry about that. F of x is sine of x. F prime of x equals cosine of x. So what should the second derivative look like? So we know, as we figured out, that where it maxes out, where it's increasing and leveling out here, and then going back down to negative, it should be at a 0. Everywhere where it does that, at the maxes and mins, it should be at a 0. So here, here, and here. And then on this side, it's going to be here. And then all the point of inflections is going to be the maximum and minimums, because it's going from negative, and then it starts going less negative back to 0. So if it's negative here, it's 0 here, and it starts going down, so it's going to be at a minimum here, and then going less minimum, and then over here at this point of inflection where it shifts again, it'll be at a maximum, and everywhere there's a point of inflection, it shifts from going negative to positive at each of these points of inflection. So here's another one. And when I turn this on, that should match, hopefully. And it does relatively closely work. And so when you continue, if I shift this up, no, I won't do that with my drawing. So if I shift this up, I can do the same thing for the next one. And this f prime of x is also a sinusoidal function, of course. But if you see, it's the same. It's here 0, the same as sine of x, but instead of increasing like it is here going for sine of x, it's decreasing. So it's flipped. And what flips the and it's flipped everywhere. Where it's a max, it's at a min. Where it's a max here, it's at a min. And where it's a min here, it's at a max. So remember, when a is negative, it just flips it. So this is sine of x. So the pattern continues. So you can make the conjecture that f double prime of x is going to be negative cosine of x. And when you continue to the fifth one, you'll get sine of x. So when it asks what is going to be the 1000th, it's just like when you're finding like the square root or the I squared, and the pattern that is for I to the 4th or I to the 16th. It's the same when you're finding the pattern for the I or derivative of sine of x. So just continue that, and with 71. And if you have any questions, let me know.